So let's start to talk about satellites. So when you hear the word satellite, you're probably thinking about something like this, like the stereotypical satellite. And that's true, it is a satellite, but specifically that is an artificial satellite, so that's something that is human-made. We want to look at something called natural satellites. So these are things like the moon. Moons essentially are another way of saying satellites. So for example, our moon, that is Earth's satellite. So we're going to look at how we can calculate some things based on us knowing from Newton that the centripetal force is provided by the force of gravity for objects in orbital motion. So what we're going to look at is satellites doing orbits. So we are going to start with this Fc equals Fg. This is pretty much our starting point for all orbital motion questions. All orbital motion questions, this should be the very first thing written, Fc equals Fg. So what we're going to try and look for is we're going to try and find the speed of a satellite that's undergoing orbit. So again, I'm going to use m for the mass of the satellite, so the object that's orbiting, and big M for the body that's being orbited. So centripetal force, we're going to use little m times v squared over r, because it's the satellite doing the orbiting. And then we have to look at the force of gravity between them. So we have big G, both of our masses, and then that distance between them squared. Well, we can certainly cancel off the mass of the satellite. And then, of course, I have this r and r squared. Well, one of these r's is going to cancel one of these. So this all condensed down to v squared equals gm over r, or v equals gm over r. What this gives us is the speed of an object that is orbiting around a body. So we could take the universal gravitational constant multiplied by the mass of the object being orbited and divided by the distance between the two objects and square root that. That is another way to give us orbital speed. So let's apply that in context. So we got Io. It's Jupiter's fourth largest moon. It has an orbital radius of 4.22 times 10 to the 8 meters. So Jupiter's mass is 1.90 times 10 to the 27 kilos. We would like to determine Io's orbital speed. Now for all these type of problems, I would expect you to show the derivation. Like I don't want to see v equals square root gm over r. I want to see how you got that. So for all these problems, the first step is going to be Fc equals Fg. Now the form of Fc that you're going to take, pick the form that's most useful. If you have period given to you, use centripetal force in terms of period. If you are looking for speed, use centripetal force that has speed in it. So in this case, I want to find orbital speed, so I'm probably going to use mv squared over r. So I'm going to use little m for Io, and I'm going to use big M for Jupiter. So I got the mass of Io, since it's doing the orbiting, times v squared over r, and we got g mm over r squared. So once again, the mass of Io is entirely irrelevant here. That r is going to get rid of one of these. So I'm going to get v squared is equal to gm over r, or Io's orbital speed is just the universal gravitational constant times the mass of Jupiter divided by orbital radius, all square rooted. So let's calculate that. So we get that. We have the mass of Jupiter. And we divide that by this radius, 4.22 times 10 to the 8 meters. So let's calculate the orbital speed of Io in this case. So we're going to do this, and we're going to get about 1.73 times 10 to the 4 meters per second. So Io's orbital speed around Jupiter, it's about 17.3 kilometers per second. So it's traveling quite quickly. So that's a very common type of question, getting you to get orbital speed using that information. Now, the other thing that we could throw in to trick you, we're going back to the whole force of gravity and Newton's law of universal gravitation. Sometimes we're going to start to talk about the height from the surface. We're going to talk about the altitude. Because remember, when we are doing calculations, we're doing it from the center. That r value is from the center of the two objects. So if we want from the height of something, we better account for that. Now, let's have a look at how this is going to work in this context of this problem. So we got PhysSat. It's a satellite that beams the love of physics to people on Earth. So PhysSat takes 135 minutes to complete orbit around Earth. So we want to find the height above Earth's surface. So what we're really looking for here is we're looking for the altitude. Now I am given the period of 135 minutes. I would like this in seconds, so we are going to multiply that by 60 and we're going to get 8100 seconds. Now so basically here's what we have going on here. So here's Earth, here's our lovely satellite out in space, and what we're going to find here is we're going to find that R value. So if I take my radius, so that is my R value. But I'm not interested in that. I'm interested in this piece here, the altitude. So I'm going to have to subtract off Earth's radius. Now you might say to me, well, Earth's radius is not given. It's not right in the question, but it is on the data sheet. Everything about Earth is on your data sheet, so look for it there. But first of all, I'm still going to calculate this R. We'll deal with the altitude part later. So my starting point for this is going to be Fc equals Fg. The centripetal force is provided by the force of gravity. Now in this case, because I have period, I'm going to want to use an equation that has period, or says that has centripetal force as a function of period. So we have this 4 pi squared r m over t squared. So m is going to be my satellite, and then big M is going to be Earth. We'll just do that. So the satellite's the one going in the circular orbit, so we'll use the little m there. And then big G times both masses divided by r squared. Right, so I can cancel out mass of the satellite. It's irrelevant. Now the objective here, first of all, is I want to calculate the radius. So I have something that looks like this right now, and this looks pretty awful. What we're going to do, much to the chagrin of your math teachers, to simplify this, is we're going to cross multiply. So first of all, I'm going to multiply these two pieces here. So I'm going to multiply 4 pi squared r times r squared, not r cubed. So we're going to multiply those pieces together, and we're going to get 4 pi squared, and then r times r squared is going to give me r cubed. On the right here, I'm going to do gm multiplied by t squared, which is going to give me gmt squared. This mass being the mass of the Earth. So as I said, I'd like r, so I'm going to divide both sides by 4 pi squared. And I'm going to get this lovely looking thing here. So I'm going to get this r cubed is equal to gmt squared over 4 pi squared. Now we're used to dealing with a lot of something squared equals another thing. This time we have an r cubed. To get rid of a cube, we need to take the cubic root of both sides. So that's one way of doing it. If you don't like cubic root, another thing we could do, cubic root of x is the same thing as raising this to the 1/3 power. So if you don't want to take the cubic root of this mess here, just raise all of this to the 1/3 power. The choice is yours. So r is going to be the cubic root of this gmt squared divided by 4 pi squared. So there's a lot that we have to punch in. There's a lot that you have to be careful with. Or I'll write this like this. So we can do either of these. 4 pi squared to the 1/3 power. Whichever method you prefer, do yours. I'm going to do this one on the left here. So the cubic root of all this, or actually I'll do the cubic root last. So I got the universal gravitational constant. I have the mass of the Earth. I can't remember what it is in the data sheet. There's two I've learned over life, 5.97 and 5.98 times 10 to the 24 kilos. So if I picked the wrong one, apologies. We have that period of 8100 seconds, and we're going to square that. And then we're going to divide this by 4 pi squared. And then we're going to cube root all that. So we have a lot in the calculator that's going to get punched in. So we've got to be really careful with this. And let's see here. A lot going on. Okay, I got my cubic root function ready. So I got my 6.67 times 10 to the minus 11. I have my 5.97 times 10 to the 24. I have my 8100 seconds squared. And the big mistake here, and a lot of students make it, watch out for that 4 pi squared in your calculator. Put brackets around it because you want this whole top to be divided by 4 pi squared as a whole. You don't want this top part to be divided by 4 and then be multiplied by pi squared. So put your brackets around that. So what I'm going to get for this, so I'm going to get about 8.714 times 10 to the 6 meters. Now that's great, but what I would like is I would like the altitude. So the altitude is going to be that radius minus this radius of Earth. Again, the radius of Earth is on the data sheet. I don't remember the exact value, if it's, because I've learned 2 in life, if it's 6.37 or 6.38 times 10 to the 6 meters. I'm going to go with 6.37. If I'm wrong, apologies, it is what it is. So if I do that, I'm going to get about 2.34 times 10 to the 6 meters. So the altitude of this satellite, or this height of the satellite from the surface of the Earth, it's about 2.34 times 10 to the 6 meters, or we'd say it's about 2,344 kilometers if we like kilometers. All right, the last thing I just want to talk about quickly, I know we've covered quite a bit, but just one more thing, and it has to deal with this whole determination of masses of celestial bodies. So somebody might kind of say, well, how do we determine that? So Earth's mass, we have it as about 5.97 times 10 to the 24 kilos. And you'd be very fair to ask, like, how do you get that? We don't have like a giant astronomical scale to stick under the Earth, plunk the Earth on it, and then read the scale. Doesn't work. Once again, though, it's Sir Isaac Newton that comes to the rescue. So he, again, using the whole knowledge of the force of gravity provides a centripetal force on objects moving in an orbit, he was able to use that to determine the mass. So we're going to use this equation here, this form of the centripetal force, that 4 pi squared mr over t squared. And we're going to look at the Earth-Moon system because we know the Earth and has a satellite, the Moon's going to orbit it. So we'd like to use some information about that system. So the centripetal force is going to be for the Moon and the Earth. So I'm going to use m for the Moon, little m, big M for Earth. So for the centripetal force, we have 4 pi squared r times the mass of the Moon divided by the period squared. And then this is going to be equal to g, mass of the Moon, mass of the Earth divided by r squared. As always, the mass of the object orbiting is going to cancel out. And then I am going to have, you know what I'm going to do? I'm going to cross multiply again. So I'm going to multiply this 4 pi squared r with r squared. I'm going to get 4 pi squared r cubed, and then I'm going to multiply this g times mass of Earth by t squared. So I'm going to get this. My objective is to determine the mass of the Earth. So I want this m, we're going to divide both sides by gt squared. So what this is going to do is this is going to give me an equation for the mass of the Earth. We have this 4 pi squared r cubed over gt squared. So this is a mathematical way for determining the mass of a celestial body. You need a body that's being orbited, you need the object that is orbiting it, you need the distance between the two, you need the mass of the body that's orbiting, and you also need the period. You need to know how long it's going to take for that object to orbit around. Now, these distances are not something people would commonly know, so this is something you'd be provided. So the distance between the Earth and the Moon, or the orbital radius, is about 3.844 times 10 to the 8 meters. And the Moon's period of rotation around the Earth, it's about, I think it's about 29.5 days, or in seconds we get 2.38 times 10 to the 6 seconds. So let's use this equation to determine a theoretical value for the mass of the Earth. So we got that 4 pi squared, we have that orbital radius, and we're going to cube that, and then we have that universal gravitational constant. And then, of course, we have our period in seconds, at 2.36 times 10 to the 6 seconds, all squared. So again, a lot to punch in, cubes, squares. Make sure you're bracketing accordingly. You don't want the brackets to mess you over on this one. So we're going to be really careful and methodical in our calculations. So if I'm very careful, what am I going to get here? Hopefully something close to the actual answer. That would be very nice. So what I'm going to get is I'm going to get about 6.04 times 10 to the 24 kilograms. 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 Now you might say, well, it's not quite 5.97 times 10 to the 24 kilograms. You're correct. But given the fact that I got very close, like what is the percent discrepancy on this? Like if I calculate that, it's going to be pretty small. Yeah, like I'm getting about a 1% difference between the theoretical and the actual. That's substantially good. Because keep in mind, in this problem, we just pretended the Earth and the Moon were isolated and nothing else existed. So by ignoring pretty much the rest of the universe, we got within 1%. I'd say we did a good job. So this is sort of a methodology of how we can determine the mass of the planets. Maybe one day we'll build an astronomical size scale, but we haven't quite got that far yet.